Roughly 240 million years have passed since the dawn of the dinosaur era, marking the beginning of the late Triassic period. Our planet bore little resemblance to its current form during this ancient epoch. A colossal landmass known as Pangaea dominated the Earth's surface, while unstable weather patterns, intense volcanic eruptions, and emerging life forms struggled to establish themselves in new ecological territories following another catastrophic mass extinction. Within this turbulent setting, archosaurs made their first appearance, a reptilian lineage that would eventually give rise to both modern crocodiles and the magnificent dinosaurs. These primordial dinosaur ancestors displayed relatively modest proportions, walked on two legs, and likely possessed warm-blooded metabolisms. Their distinguishing characteristics weren't related to body size, but rather centered on their unique pelvic anatomy and locomotive patterns. These creatures demonstrated remarkable efficiency in movement and speed, and mounting evidence suggests they possessed considerable intelligence, as contemporary research increasingly reveals sophisticated social structures and behaviors. The arrival of the Jurassic period marked a transformative phase. Continental masses initiated their gradual separation, atmospheric moisture levels increased dramatically, and plant life experienced unprecedented growth. This epoch represents what scientists consider the pinnacle of dinosaur dominance. Massive sauropods emerged during this time, colossal beings such as Brachiosaurus that achieved weights measured in multiple tons alongside theropods, including the renowned Allosaurus. Evolutionary pathways diverged in multiple directions. Certain dinosaur lineages pursued ever-increasing size, while others refined their velocity, auditory capabilities, and visual acuity. This period witnessed not merely the coexistence of hunters and plant-eaters, but rather a sophisticated equilibrium among diverse biological entities. These phenomena persisted across millions of years, occurring long before humanity's emergence on our planet. In contemporary discussions about dinosaurs, our thoughts typically gravitate towards cinematic portrayals, digital entertainment, and museum exhibitions displaying weathered remnants from bygone eras. However, few individuals contemplate the actual origins of these fossilized chronicles. Which researchers, and in what remote locations across our globe, excavated femur bones comparable in length to human stature? Who successfully extracted petrified eggs from solid rock formations? Which hands carefully held Tyrannosaurus teeth as though handling artifacts from extinct mythologies? The moment has arrived to investigate where our planet most powerfully echoes with the voices of prehistoric reptiles and to understand the specific reasons behind these geographical concentrations. Mass burial phenomena, dinosaur necropolis sites. Contemporary paleontological investigations increasingly reveal what researchers term dinosaur graveyards, authentic geographical locations where multiple dozens or hundreds of skeletal remains became entombed through singular catastrophic events, including river sediment accumulation, volcanic explosions, or flash flooding incidents. These collective burial sites provide scientists with opportunities extending beyond reconstructing individual specimens bone by bone, enabling complete community restoration and detailed understanding of these creatures' lifestyles. Researchers can determine predator-prey relationships and identify those specimens that potentially perished through accidental circumstances rather than predation. Understanding the geographical distribution of dinosaur bone discoveries reveals increasingly fascinating patterns. Beneath terrestrial layers lies systematic organization, specifically geological organization. Each contemporary location-yielding dinosaur remains represents an intricate combination of prehistoric climate conditions, geographical features, tectonic plate movements, rock formation types, and naturally, the persistence of archaeological investigators. Let us systematically examine this stratified terrestrial composition. Geological prerequisites for dinosaur preservation. Sedimentary rock formations constitute the fundamental requirement. Dinosaur remains do not occur within granite formations or volcanic tuff deposits. Instead, they are preserved within sedimentary materials, sandstone, mudstone, limestone, and shale formations. The explanation lies in the formation process of sedimentary rocks in areas that once contained rivers, lakes, deltas, floodplains, and lagoon systems. These environments established optimal conditions for organism burial. Gentle sediment accumulation, rapid corpse covering with silt or sand particles, and oxygen-depleted conditions collectively decelerate decomposition processes. Reduced oxygen availability increases the probability that organisms will undergo mineralization rather than complete destruction, resulting in fossil formation. Unfortunately, this preservation method proves ineffective for modern media. Mesozoic-era climate conditions represent the second critical factor. Throughout the dinosaur age, particularly during the Jurassic period, global temperatures significantly exceeded contemporary levels. Polar ice formations were non-existent. Mean temperatures remained elevated, while atmospheric carbon dioxide concentrations reached nearly quadruple current measurements. These conditions established consistent, moisture-rich, warm environments across extensive land areas, including barren coastal regions. Remarkably, present-day desert and steppe regions once supported tropical forest systems and marshy flatlands, optimal habitats for large herbivorous species and their predatory counterparts. The Gobi Desert exemplifies this transformation. During the late Cretaceous period, it consisted of interconnected grasslands, lake systems, and dune formations receiving seasonal precipitation, essentially a Mesozoic savanna ecosystem. Climate patterns and sedimentary deposits alone do not account for all preservation factors. Tectonic plate activity plays an essential role. Throughout the preceding 200 million years, continental positions have remained dynamic. Pangaea fragmented, continental drift commenced, mountain ranges emerged, and new oceanic basins formed. Nevertheless, in specific locations, geological structures developed such that rock layers of appropriate age remained at surface levels or shallow subsurface depths, avoiding destruction through mountain building processes. The North American continental platform demonstrates remarkable stability. Major deformation events have not occurred since the Cretaceous period, leaving sedimentary layers containing dinosaur remains essentially undisturbed. Similar conditions exist in China's Liaoning region, where moderate tectonic activity combined with beneficial volcanic eruptions. Ash deposits rapidly covered small feathered dinosaur carcasses, creating instantaneous burial effects. These volcanic events literally preserved ancient fauna. Modern paleontological activity represents the final crucial element. Realistic assessment acknowledges that bone existence alone proves insufficient. Discovery remains necessary. Not every nation possesses adequate resources, technology, field archaeology traditions, and political stability required for conducting large-scale excavation projects spanning decades. Certainly, several countries maintain comprehensive capabilities, established scientific institutions, universities, museums, and most critically, systematic governmental and private funding support. Researchers from these nations actively collaborate, publish findings, and transfer discoveries to museum and research collections. This consistent, thorough approach generates discovery statistics. Why specifically these locations? Because multiple factors converged simultaneously: ancient river systems and soft silt deposits, warm climate conditions, stable tectonic activity, and in our era, dedicated individuals willing to invest decades systematically uncovering geological history. Global distribution: dinosaur presence across all continents. Initial impressions might suggest dinosaurs represent the exclusive heritage of select fortunate Earth locations, but deeper investigation reveals dinosaurs as genuinely global organisms. Their fossilized remains have been discovered on every modern continent without exception. Let us methodically examine all continents with archaeological precision. Asian discoveries. Asia constitutes a genuine treasure repository for recent decades' discoveries. Mongolia, particularly the Gobi Desert, has provided science with complete nest structures containing eggs, exceptionally preserved theropods, and even behavioral scenarios: predators attacking Protoceratops, frozen by death during combat moments. China, especially Liaoning Province, became paleontology's revolutionary epicenter following feathered dinosaur discoveries, transitional forms connecting theropods and birds. Fossil specimens preserving soft tissue impressions, feather structures, and even pigment traces were also recovered there. North American findings. North America ranks among the earliest and most thoroughly investigated regions. Hundreds of species have been identified here, including iconic forms such as Triceratops, Tyrannosaurus, and Ankylosaurus. The geographic area spanning Montana to Alberta represents ancient river systems where mass burial events occurred regularly. American paleontologists initiated research during the 19th century and continue discovering new species annually. South American discoveries. South America, primarily Patagonia, yielded the largest known dinosaur species, sauropods including Argentinosaurus and Patagodoton. These specimens exceed forest dimensions, not to mention museum capacity. South America also proves significant for harboring some of the most ancient dinosaur species, such as Eoraptor, a primitive lightweight predator from the late Triassic period. These discoveries enhance understanding of dinosaur evolutionary origins. African excavations. Africa represents a continent where paleontological development continues, yet has already produced numerous significant discoveries. Egypt, Morocco, and Niger constitute territories where Spinosaurus, Carcharodontosaurus, and numerous other forms were uncovered. The Sahara during the Mesozoic period was a verdant, productive plain, and bones in these locations resemble forgotten correspondence from a submerged world. Africa represents the convergence point for southern and northern faunas, making this region particularly important for understanding species migration patterns. European contributions. Europe maintains less paleontological prominence, but extreme importance. For instance, England produced the first scientifically recognized dinosaur discoveries during the early 19th century, where the term dinosaur itself originated. Germany contributed Archaeopteryx, the transitional form connecting dinosaurs and birds, featuring both feathers and teeth. France, Portugal, and Romania have yielded both terrestrial and marine reptile specimens. Europe functioned as an archipelago during the Cretaceous period, consequently producing dwarf dinosaur forms adapted to restricted island ecosystems. Russian territories. Russian contributions merit recognition. The Chita region has produced predatory theropod bones from the Cretaceous period. The Amur region, particularly near Kundr village, has revealed duck-billed dinosaur, hadrosaur, remains, including well-preserved skeletal structures. The Crimean Peninsula has also yielded dinosaur tracks, primarily footprint evidence. Siberian regions, specifically the Kemerovo area, have produced sauropod skeletal fragments and other herbivorous dinosaur remains. The Volga region, particularly the Ulyanovsk area, is known for plesiosaur and ichthyosaur discoveries, marine reptiles contemporary with dinosaurs. Australian evidence. Australia was historically considered dinosaur poor, but recent decades have transformed this perception. Queensland and Victoria have yielded both herbivorous and predatory forms, including megaraptors and iguanodonts. Australia's geographical isolation provides compelling evolutionary examples separate from global patterns, while also demonstrating connections with Antarctica and South America during pre-drift periods. Antarctic discoveries. Antarctica presents the most remarkable case. Despite current ice coverage measuring kilometers in thickness, during the Mesozoic period it comprised part of the southern supercontinent Gondwana, warm and forested. James Ross Island has yielded dinosaur fossils, including hadrosaur specimens. These discoveries remain rare and difficult to access, yet prove extremely significant. They demonstrate dinosaur adaptation even to polar environments. Consequently, dinosaurs achieved global distribution across all continents, within all climate zones, exhibiting diverse forms and lifestyles. We typically conceptualize them as distant and separate entities, but reality demonstrates they maintained closer planetary relationships than any preceding life forms. Their traces exist everywhere, wherever shores, deltas, or sandy spits once existed. They inscribed their presence across Earth's complete geological map. Continental unity. How Pangaea explains global distribution. How does such global distribution become possible? Observing contemporary globes or world maps, continents appear inaccessible to us. Bicycle or swimming transportation proves impossible between continents. Africa, America, Eurasia, Antarctica, Australia, yet this perception represents merely a geological moment's illusion, a brief instant within planetary history scale. Truth reveals that Earth, this temporal stone vessel, has never remained stationary. Like all living entities, it has experienced cyclical phases. Formation, merger, fragmentation, plate movement, and new oceanic development. Examining the stratified depths of archaeology, paleontology, and geology with dedicated persistence, scientists reconstruct one of planetary history's greatest events, Pangaea's dissolution, that unified supercontinent once connecting nearly all terrestrial landmass. Scientific consensus indicates Pangaea's formation approximately 335 million years ago during the late Paleozoic, representing the climax of continental convergence cycles. Its designation, All Earth, carries intentional meaning. Magnificent in scope, extending from northern to southern latitudes, it unified what now spans hundreds of millions of kilometers: North and South America, Europe, Africa, Asia, Australia, and Antarctica. However, like all significant unions, Pangaea's unity proved temporary. Within Earth's mantle, that profound, heated, viscous substance containing convective currents, forces developed beyond civilizational or planetary cycle control. Approximately 175 million years ago, the Jurassic period initiated a nearly imperceptible yet fateful process: fragmentation. Initially, Pangaea divided into two primary segments, northern Laurasia and southern Gondwana. Laurasia encompassed future North America, Europe, and Asia, while Gondwana included South America, Africa, Antarctica, Australia, and the Indian subcontinent. Gradually, across tens of millions of years, continued fragmentation occurred, with segments sliding across lithospheric plates like icebergs on slowly flowing magma oceans. Approximately 130 million years ago, South America began separating from Africa, marking the Atlantic's birth, then a narrow, volcanically active seaway. Against these massive geodynamic transformations, life developed. Paleontological observation cannot withdraw from the stunning tableau created by the Mesozoic, the reptilian era. Dinosaurs, emerging during the late Triassic, had already confidently populated most terrestrial biomes by Pangaea's fragmentation onset. Their distribution benefited from initial landmass integrity, evolutionary progression, adaptation, and geographic isolation. Jurassic period commencement brought climatic changes. Pangaea's fragmentation created new oceanic currents, establishing new climate zones, monsoon patterns, humid regions, and arid territories. Biome fragmentation accelerated evolution and initiated isolation-driven endemism. Where unified forms previously dominated, new variants emerged, adapted to localized conditions. Jurassic period witnessed Diplodocus and Apatosaurus prosperity. Forest environments supported Allosaurus hunting, while pterosaurs glided above ancient seas. Cretaceous period produced ankylosaurs, horned ceratopsians, formidable tyrannosaurs, duck-billed hadrosaurs, and countless other creatures. Despite their formidability and diversity, dinosaurs remained products of their temporal context, an era when tectonic mobility gradually but inevitably led toward new realities. As continental separation increased sufficiently, climate diversified, flora transformed, and ecosystems gained complexity. Biology terms this phenomenon divergent evolution. By the Cretaceous period's conclusion, approximately 66 million years ago, global geography approached recognizable configurations. South America and Africa achieved separation. The Indian subcontinent approached Himalayan collision. North America assumed recognizable triangular form. At this juncture, a particular catastrophe, possibly another extinction event, concluded the dinosaur era, leaving behind ash deposits, geological layer scarring, and new chapter initiation. Perpetual motion, ongoing continental movement. Remarkably, Pangaea's fragmentation did not conclude then, it continues presently. The Red Sea expands, East Africa gradually separates, the Atlantic widens, and the Pacific contracts. Indeed, continents continue floating on mantle material and will persist as long as Earth exists. Reflecting on this incredible narrative, we recognize dinosaurs as living historical mirrors, reflecting their era's complex processes, changing climate and Earth's tectonics, life, and environment interaction. They dominated for millions of years, becoming giants and adaptation masters, but ultimately yielded to new life forms. Perhaps hundreds of millions of years hence, a new supercontinent will again unite scattered lands, Pangaea Ultima, a new Amasia, as geophysicists theorize. Future archaeologists then, possibly tentacled aliens dwelling beneath different stars, examining long-deceased creature bones, will with identical awe and admiration excavate the past, attempting to understand Earth's transformation when we still existed here.